Oh, okay. Today's shoot very xiong.
Sure.
Okay, let's take a break.
Okay, take five.
Yeah.
Okay.
Stomach aches, yeah. Don't know can fart here or not. It's okay lah, I don't think he will find out. Let me go for a quick one. Huh?
Hey, William, what did you just do?
No, what? I didn't do anything.
You look at your order. How to film like that?
Sorry.
Wow, you power. That was a powerful fart, man.
Yeah, so don't mess around with me, because anytime I can.
What? Hey, don't relax.
Hey, anyway, you know what's the chemical component of farts or not?
Wow, you like that also can link to chemistry.
Of course lah.
Okay lah, so the chemical ingredient in fart, many, one of them is methane, CH4.
Oh, methane, okay.
Yep. So you know how to draw the structure of methane now? Because that day, a student was asking me.
The structure of methane?
Yeah,
of course. Right, methane is CH4,
Yep,
right?
yep.
So I'm going to draw it quickly right now. Okay, so we have carbon, then we have the hydrogen, another hydrogen, another hydrogen, and another hydrogen. Simple, right? Structure of methane, CH4.
You sure that's the correct structure now, William?
Isn't that correct?
Wow, no wonder your fart so smelly. I think you need to revise on your VSEPR. Wow, William, just now your drawing CMI. This is the true arrangement of methane. It's tetrahedral arrangement, okay?
Okay.
So this is covered in the VSEPR theory.
Oh, VSEPR.
Yeah.
Something we did last week with the class, right?
Yep.
Alright, so maybe let's flip to our
Encyclopedia.
All the stuff are there. Alright, so if we flip to our encyclopedia, I think last week we spent a long time with the students telling them how VSEPR actually works.
Yep.
So Mr. Yap, do you mind just recapping for us what's the idea behind VSEPR?
Right, so the first thing is of course to get a correct dot and cross diagram. But after that, you guys have to ask yourself, around the central atom, how many numbers of regions of electron density are there? So in our syllabus, we're going to focus on a few of them. So namely 2 electron density, 3 electron density, 4, 5, or 6.
Right, so the whole idea behind the VSEPR theory is to really break down the table into segments, right?
Yep.
And each one of them has different number of electron densities around this, right? And we did explain the rationale. What is the most important thing is to focus on what we call the basic shape and the basic angles, all right? So we just quickly run through this with them again, right? So in an event, a central atom has 2 regions of electron density around them. And the main idea is they want to minimize repulsion between them. Electrons, they don't like each other, so they will find the furthest angle they can from each other. So when you have 2 electron densities around yourself, then the greatest angle you can be is 180 degrees, which kind of explains why this thing is like linear in shape. Now, if you have 3 electron densities around the central atom, then they will adopt 120 degrees, which is a trigonoplanar. If you have 4, then 4 will be tetrahedral, 5 will be trigonal bipyramidal, and 6 will be octahedral, right? So the rationale behind the basic shape is always the fact that electrons, they want to be as far apart as possible, right? I think we're not going to recall everything for them. Maybe we just focus on one of the blocks. Okay, what's the favorite number here?
4.
Okay, 4, right. So we're just going to use the blocks of 4 to recap how the VSEPR theory actually works. Now, if you look at the table of 4, you do notice the first shape that we have is you have 4 bond pairs. So as Mr. Yap is showing over here, 4 bond pairs is going to adopt this tetrahedral arrangement where you expect the bond angles between every single bond to be 109.5 degrees, right? And rationale being, this is the furthest angle they can be away from each other. Now, in an event, you have another dot and cross diagram where you take one of the bond pairs and you replace it with a lone pair. So you can imagine, all right, there is a lone pair that is over here, but what do we focus on is we only focus on the bond pairs that are left behind, right? So if you take a close look at the bottom, you will see that there's this triangle base. All right, and then the whole thing actually rolls up into a pyramid, which kind of explains the shape that we have here. In an event, you have 3 bond pair as well as 1 lone pair. The shape that is left behind is called trigonal pyramidal. Now, bear in mind, shapes are always with respect to the bond pairs. Just ignore the lone pairs when you deduce the shape. All right. Now, Mr. Yap, if you take a close look at the angles, you do notice that the angle is actually changing from 109.5 to 107 degrees. Why is it like this?
Right, so this falls back to our second principle of VSEPR theory, which basically states that a lone pair bond pair repulsion is greater than a bond pair repulsion. So therefore, forcing the 3 bond pairs at the bottom to be closer to each other, they are more squashed, resulting in a drop in the bond angle.
That's right? Just remember, lone pairs always exert greater repulsion, pushing the angles closer in together. Right? So the same idea, if we were to build on this, if now I have 2 bond pairs and 2 lone pairs, show your muscles, alright? So what we have right now, just imagine there are 2 more lone pairs that's sticking in and out. What is left behind now is like what we call a band shape or a V-shaped structure, right? So you can see from your notes, in an event, we have 2 bond pairs and 2 lone pairs. Now the angle will change from 107 to 105 degrees for the same reason. The moment you have more lone pairs, there will be greater repulsive effect, and that's why the angles, they will further drop down to 105 degrees. Right? So the basic assumptions, principles of VSEPR is always dealing with the need to be as far away from each other as possible, which explains the basic shape, and the fact that lone pairs, they have greater repulsion than bond pairs. So Mr. Yap, just now you mentioned that lone pairs, they have greater repulsion than bond pairs. Can you share with us the reason why?
Mr. William, you always ask the very good questions, but the answers are always in our notes.
Always in the notes. Okay, so let's take a look at it, right?
William, so on this diagram, we have a CH4 drawn and an NH3 drawn, alright? So if you were to focus on the bond pair of the C and the H, where the electrons are shown, now I need to invite my secret weapon in to
Secret
explain.
weapon?
Yes,
Wow,
secret
okay,
weapon.
let's take a look.
Where's my secret weapon? Oh, it's here. Okay, so I'm the central atom, I'm carbon. Mr. William is going to be hydrogen, the terminal atom.
Hydrogen.
Okay, and we're going to share a pair of electrons between us.
So we're going to do a bond pair,
Yes.
a sharing of electrons.
Sharing of electrons to form a bond pair.
We have 1 dot, 1 cross,
Yes.
and we are sharing
Sharing
electrons. So
yeah.
this is what? Bond
Bond
pairs.
pair, right?
Okay, bond
so
pairs,
as you can
right?
see, I'm the central atom, he's the terminal atom. The electrons of the bond pair are confined between the 2 of us. So the electron density is spread across this region. It's localized between the 2 of us. It's stretched, it's not free to move around. Okay? Now, if I were to replace William, push him away, now I'm nitrogen, right? So focus your attention on ammonia. Now I'm nitrogen. Now I have a pair of lone pairs above me. So lone pairs, let me use another secret weapon. Okay, wow, a lot of secret weapon like a magician. All right, so this is a lone pair, right? So I'm nitrogen. I have a pair of lone pairs of electrons above me. Now, because I'm the only person holding on to this pair of electrons, so they are allowed to roam about more freely above me. So they will occupy a larger space above me because they are free to move about. So as you can see from on the screen, it looks like a pirate hat above me, right? Because they are free to roam about above me. So what this analogy is trying to say is simply that a lone pair of electrons is going to occupy a larger volume in space as compared to a bond pair. And therefore, a lone pair of electrons exert a greater degree of repulsion as compared to a bond pair.
I see, alright. Thank you for using your balloons to explain the difference between lone pairs as well as bond pairs.
Good balloons, right?
Yep, definitely.
So William, you always like to ask me all the difficult questions, right? Now my turn to throw you a difficult question.
Okay.
So is it true that all molecules with 3 bond pairs and 1 lone pair would have the bond angle of 107 degrees?
Well, the answer is it may not always be true, alright? It really depends on other variables as well. So what we learn in VSEPR is just a general framework. Okay, so I'm going to use some examples to explain this to the class. Now, I've drawn a few examples here. Let's take a look at ammonia, alright? NH3 as well as PH3. Now, what's the difference between them, Mr. Yap?
So the difference would be the terminal atoms are the same, they are all H, but the central atom is different.
Okay, so the central atom, they are different, and therefore they become our focus in this case. Now, between the 2 of them, which one is more electronegative?
Okay, so nitrogen is above phosphorus in group 15, so nitrogen would be more electronegative.
Okay, so if nitrogen is more electronegative, right, so this is written in the bullet over here, how does that impact the position of the shared electrons? Now, you can see between N and H, they will be sharing electrons, but because nitrogen is more electronegative than phosphorus, you do expect nitrogen to be better at drawing electrons towards
better
him.
at sucking the electrons to itself.
Yes, alright. So imagine, right, I'm going to draw the electrons. Now, these are the bond pairs. I'm going to draw the bond pairs of NH closer towards the nitrogen, whereas for pH, I'm just going to position them further away from the central atom. So right now, Mr. Yap, we focus on the position of the bond pairs. Now you tell us which one has a greater repulsive effect.
Okay, so if you were to zoom in onto the N atom, you would realize that the electron density is more concentrated around the central nitrogen atom. So there will be more repulsion experienced there. The bond pairs, will be pushed further apart, resulting in a larger degree of bond angle.
Right, so we just focus on the position. If they are more squashed together, then actually the repulsive effect is going to be bigger. Right, so that's why they are not exactly 107. It's give and take is 107, but because of what the concept here is what electronegativity. Right, so okay, this is one example to explain this. Now, what if we compare this this with another example. So you see your notes, there's NH3 and there's also NF3. Now, what is the difference this time around?
Right, so you can see that it's actually opposite from the above example. Now the central atom is the same, the terminal atoms are different.
So right now we focus our attention onto the terminal atoms, but the concept is still the same. It's still about electronegativity, right? So this time round, we do expect for NF, F being the one that's more electronegative. Therefore, we do expect that the electrons are now going to be closer towards fluorine as you compare with your NH. And for reasons I think Mr. Yap has explained to us earlier, the ones that are closer to the top is going to experience a greater repulsive effect, and that is why ammonia has a larger angle between them. Right? So the concept is the same. It's always about electronegativity, but your focus is to really understand, is it the central atom that's the point of focus, or is it the terminal atom that's the point of focus? All right, good.
Okay, so another factor that can explain this phenomenon of the difference in bond angle despite having the same shape is to look at what we call steric repulsion, which examines the size of the terminal atoms. So two examples, PCl3 and Pi3 drawn below. So iodine is a larger atom than chlorine, right? So you will have a larger electron cloud size. So if the larger electron cloud size of iodine, if you were to put them close to each other, they will experience a lot of repulsion, correct?
Pushing,
push,
right?
push, right? So they will push each other apart, so all the Pi bonds will be pushed further apart. So the bond angle over here, right, will be larger because the Pi bond pairs are pushed further apart. Right? So that's the idea behind steric repulsion, which examines the size of the terminal atoms.
Hey, Mr. Yap, do you know that some molecules are polar while some are non-polar?
Polar? You mean like the polar bear?
Okay. No, I mean the polar molecules.
Oh, you must be clear. I thought polar bear.
No. Okay, let's show the class how exactly it works. Now we're going to use some examples in our notes. So let's say we focus on NH3, right? So if you look at NH, now can you tell us, right, the electrons, are they equally shared?
I don't think so, because nitrogen is more electronegative than hydrogen, right? So the electron density of the bond would be therefore put towards nitrogen. So nitrogen will have a bit more electrons, so denoted by a partial negative charge. Hydrogen will have a bit less of electron, denoted by a partial positive charge. So a bond with a partial negative and partial positive is therefore said to be a polar bond because there's a dipole moment.
Alright, so if you look at NH, and we understood that because N is better at pulling electrons towards him, there is a net movement of electrons towards him. Now the same thing will be replicated for all the various NH bonds. And what you notice now is there's this like vector movement that's building up. And if you look at all three of them, they are all going up in the same direction. So eventually, when you add everything up, you will see that there is a net dipole that actually goes upwards. And this is what we term as a polar molecule. Right? Now the same concept being explained in water, H2O, right? So you do notice again oxygen is more electronegative, so the vector movement this time round is also moving in the upward direction. So this must be another example of a polar molecule.
Okay, so William, does that mean all molecules with polar bonds is a polar molecule?
Well, not quite, right? It really depends. Okay, so let me show you again some examples, right, to prove that this may not be the case. So if you go down a little bit onto your notes, you will see an example of BF3, right? So again, fluorine is more electronegative. We expect electrons to move in this direction. Another BF and another BF, right? So if you look very closely, the dipoles are going in all different directions. And if you sum up the net vector, you do realize that they actually cancel each other out. So this is an example where the bond itself is polar. You do see that there is a difference in electronegativity, but because of the position and the way that the molecule is being oriented, everything actually cancels away from each other. Okay, one more example, right? Something a bit more complicated. If you look at PCl5, now PCl5 has two different planes to it, right? The first one over here, which I'm going to shade this in green, this is what we call the equatorial plane. So if you look at the equatorial plane, you do realize that it will be the same as what we have for BF3. Everything kind of cancels away. And then the second plane that we are looking up is the up-down, which is called the axial plane, right? So if you look at the axial plane, you will see that again the up and the down, they will cancel away from each other. So there you have it, a molecule that has polar bonds, but overall it is non-polar.
So William, do you notice the trick or not?
What's the trick?
The trick is, if you go back to the VSEPR table, if you look at the basic shapes, as long as the molecule is of the basic shape and the terminal atoms are all the same, the dipole moments will definitely cancel each other out. There will be overall no net dipole, the molecule is non-polar.
So that's a shortcut. Okay, just remember, VSEPR table, the basic shapes, they are always going to be non-polar if they have the same terminal atoms. What is the purpose of all this?
Okay, William, always asking the tough questions. So we need to learn all this to determine whether a molecule is polar or non-polar, because this will bring on to the next idea of intermolecular forces of attraction. So stay tuned to that. William, I share with you a breathing technique.
Okay.
Come, we take a deep breath in,
Okay.
a deeper breath out. Oh my god, William, do you know what's inside a breath now?
I know, methane.
Oh my god, if it's methane, I think you really need to see a dentist. Okay, it's actually carbon dioxide.
Oh, carbon dioxide.
So take a guess, how many molecules of carbon dioxide are there in a single breath?
Isn't it one?
It's not one, it's definitely a lot, millions of it.
Really?
Yeah, many millions of carbon dioxide molecules in one breath.
Oh, okay.
So you want to do another deep breath out? Oh, please, contributing to global warming. Okay, anyway, so in his breath, there are millions of carbon dioxide molecules. So if we were to focus our attention on a single CO2 molecule, all right, you have to understand that between the O atom and the C atom, okay, there will be strong covalent bonds existing between them. But what is the force holding the different types of different carbon dioxide molecules together? We actually call them the intermolecular forces of attraction. Okay, so in A level, we're going to focus on three main types of intermolecular forces of attraction. The first one being ID-ID interactions, second one being PD-PD interactions, and the last one being hydrogen bonding. Okay, so in today's video, we're going to focus only on ID-ID interactions.
Right, so the first IMF we're going to focus on will be instantaneous dipole-induced dipole. The short name is called ID-ID. Right, where do we find it? You can see it's predominant in non-polar molecules. But the fact is, a lot of other metals, for example, ions, polar stuff, they also have ID-ID, but they're usually more important forces, so we tend not to focus on those. Right, what is the idea and the theory behind ID-ID? It's over here, we call this instantaneous polarization of electron clouds.
That's a very chim term, you know.
Yeah, sounds very chim, but it's okay. Let us simplify for the class. Now we're going to use a picture and a simple story to illustrate how ID-ID exactly works. Right, so you can see on your notes, it says over there, we need a molecule that has symmetrical distribution of electron clouds, which means we need something that is non-polar in nature.
Okay.
Right, so for example, it will be
Oxygen?
hydrogen. Okay, let's try again, right? So for example, it will be
Hydrogen.
oxygen. Okay,
Okay,
one last time,
alright.
right? So for example, it will be hydrogen. So when you look at hydrogen, you will know that they have two electrons and the two electrons are equally shared between them, right? So what do we expect? We expect one electron on the left and one electron on the right. So we have this symmetrical distribution, right? So whatever molecules you are, so long as you are hydrogen, we do expect in the long run the electrons to be distributed this way. Okay, but bear in mind something. How do electrons move, Mr. Yap?
They are always moving and the movement is random.
Alright, good. So the key is electrons are always random in their movement, right? So if they are random in their movement, will there ever be a chance, a split second where you don't have symmetrical distribution?
Yeah, there could be a particular point in time whereby maybe one side got more electrons, one side got less electrons by chance. Yes, that's entirely possible.
Yep, so remember, the key thing is by chance. Electrons are moving randomly, so there could be an occasion where you have 2 electrons on one side and 0 electrons on the other side. So naturally, the side with more electrons is going to acquire a delta minus, and the side with lesser amount of electrons is going to acquire a delta plus. Now, what is this going to impact? This is going to impact the surrounding molecule. So you can imagine, the moment there is a delta plus that's building up here, it will induce or polarize the neighboring molecule to now have a delta minus. And the reason for this is the plus and the minus can then do an attraction between each other. So the attraction that's formed between them has a name, which is called instantaneous dipole-induced dipole, or in short, we call this ID-ID interaction. So it's kind of like an electrostatic attraction between the two of them, right? And what we are showing you here is only 2 molecules, but bear in mind, as we saw earlier on in CO2, there are like millions of CO2 that's side by side. So this is going to create a wave or a chain effect. So you can imagine this is going to be extrapolated throughout the entire millions of molecules that's side by side.
Alright, William, that was a very long grandmother story. Okay, so if you guys turn to the next page, the key points are summarized over there. So let's just take a quick look. So the important thing is to recognize that the electrons, they are always moving. Okay, so that at a particular point in time, there might be an unequal distribution of electrons, causing one molecule to have a dipole moment. Alright, so this dipole moment will make a neighboring molecule have a dipole moment, and the ID-ID interaction is simply the attraction between the delta minus on one molecule and the delta plus of another molecule. So this is at one particular point in time. So at the next instant, this force will break and it will reform at another area, and this process just keeps repeating. So we always say that such attractions are weak and short-lived, and they are always forming and breaking all the time.
Right, so I think the main idea is IDID is by chance, and it doesn't last for very long periods, right? Because electrons' movement is very random, and they will only last for split seconds.
Right. So William, you know, every time when we study for a particular force or particular interaction, right, we always have to ask ourselves, what are the factors affecting the strength, right?
Right.
So, are you going to go through that with me today?
No, because we don't have time.
Oh,
no. But it's okay, we're going to leave it to our teachers.
Okay.
We'll go through the factors of IDID plus the other bondings like permanent PDPD and hydrogen bonding.
Yep.
Right, so we will see you in class then. But before we go, remember who we are. We are the Chemical Bonding Brothers!